What did we do yesterday? Yesterday I solved two examples. Two example problems. One was type 1 and the other was type 2. Please make sure you understand the approach while you solve these two problems. The type 2 problem that I solved, that is a question on set 6a. So in the next tutorial I am not going to revisit that question. I have spent enough time on that. So that completes set 6a. On Tuesday I will be there in the classroom for the tutorial session. If you have any doubts, if you have any specific questions, I will be willing to answer. But from my side, set 6a is complete. I have nothing else to explain on my own. Type 1 problem that I solved, that is not on set 6, but that's also a very good problem which will help you understand the concept. So based on these two examples that I solved yesterday, I hope you will be able to solve the set 6b unsolved problems. Okay. Now what do we do next? The first topic that I want to discuss today is what are called dynamic reaction forces. Dynamic reactions, forces or torque. Dynamic forces, dynamic torques. In a combined way, I'm saying dynamic reactions. I'm going to explain that, what we mean by dynamic reactions. Also going to talk about what is called rotor balancing. In fact, I will use the example of rotor balancing to explain what dynamic reactions are. Let us consider a rotor. Okay, so this is what I am calling as the rotor. I have an RB of mass m and there is a massless rod welded to it, which I am highlighting right now. This whole thing is supported at P and supported at Q, and this massless rod plus RB has this freedom to rotate with angular velocity omega the way I have shown. So this massless rod plus RB I am calling as a rotor. Okay. So it is given that omega mi, I is the inertial frame, the ground frame, is given that omega mi is omega times E3. E3 is this direction. Also, it is clear from the figure also, I have tried to show it, that dE3 dTi is 0. So if I have to solve anything about this problem, I know by this time itself that it is going to be a type 2 problem. I haven't defined the problem statement, but any analysis of this situation, I will categorize that as type 2 problem, and I know that at sooner or later I will be applying MESA V2 on it. It's also given that omega dot mi is 0. So omega is constant. C is the center of mass, and the way I have drawn it, the center of mass is not lying on the axis of rotation. Now remind yourself what is meant by axis of rotation. Like 10 classes ago I defined axis of rotation. You can go back and check. So PQ is the instantaneous axis of rotation of the RB given. However, center of mass is not lying on that, not lying on IAR. IAR is instantaneous axis of rotation. There is an offset, and that offset is, let's call that offset R. This distance, you see, this distance. Distance of C from IAR. Okay. Also it is given that this length is L1 and this length is L2. So you exactly know where the center of mass of the RB is lying. It is not equidistant from PQ, and it is not on the axis of instantaneous axis of rotation. It's also given that P and Q, which are supports, can offer only two force components each. And those force components are not along IAR. It will become more clear when I draw the free body diagram. So P and Q cannot offer any torque, offer any reaction torque. They can offer only force components, and that too force components in the non E3 direction, either E1 or E2 direction, but not in E3 direction given. What do we have to find? I want to find reaction forces at P and Q. Reaction force system at P and reaction force system at Q. This is what we need to get. Alright. So since this is a type 2 problem, I am going to choose my coordinate system such that its third axis will be along E3 and x1, e1, x2, e2 will be perpendicular, will form a plane perpendicular to E3 as it should. So let me draw that here. Choice of working coordinate system. We'll call it step 1, just like I was identifying various steps in my approach. Step 1. Step 1 was judge type 1 or 2 that we have judged. It is a type 2 problem. Step 2 was Identify your working coordinate system. This is my working coordinate system. C x1 e1, x2 e2, this is the coordinate system I choose. P, this is Q. It is body fixed as it should be, that we have discussed earlier. Okay, that's step number 2. Step 3, draw the free body diagram. This is the instantaneous axis of rotation. This is C. At C I have of course mg acting. At this instant it is acting along minus E2. At this instant. What forces I should put on this? What other forces? This is the massless part of the body. At P, I have been said that the support is such that it cannot generate any torque. So I will not put any torque at P, any reaction torque. I have been told that at P forces can be generated, but they do not have any component along E3 direction. This is the E3 direction. So it means I am going to put P1 and P2. Okay. This is along E1 and this is along E2. You can look at the orientation of my working coordinate system here. P1 and P2 are unknown scalars. Unknown. I will find them. At Q, the story is the same. Q is capable of generating only Q1 and Q2. Any other force I need to put on my free body? No, that's all. These are the forces that are acting on the RB at this instant. Step 4. Euler's first axiom. Euler's first axiom tells me that P1 E1, P2 E2, Q1 E1, I'm talking about net force acting on my RB, plus minus mg E2. This is the net force. I have accounted for everything. That must be equal to mass times the acceleration of the center of mass with respect to I. What is the acceleration of center of mass? Look at the figure. Know that this distance, this offset is r, rotating with omega, no omega dot. What would be the acceleration of point C at this very instant? I did ask the same question in the last tutorial for a different problem, but situation was similar. What will be the acceleration? The acceleration will be omega square r what would be the direction? Direction will be E2 plus E2. Right now E2 is vertically upwards. This gives me three equations. What are those three equations? The three equations are P1 plus Q1 is 0. Let me call it equation number 1. The second equation is P2 plus Q2 equals mg plus m omega square r. Mind you, this r and this r, they are same. I don't do it intentionally, but I end up writing both types of r in the same problem. Alright, I get two equations. If you do care to count the number of unknowns, now third equation in this case is actually 0 equals 0, trivial case. I won't number it actually, trivial, along E3. There is nothing along E3 actually at this instant. Neither there is any force nor does the acceleration has any component. Two relevant equations I have, two non-trivial equations I have. If you count the number of unknowns, we have P1, Q1, P2, Q2. 4 unknowns and 2 equations. Mind you, in this case omega is a known quantity. I did mention omega here. I should have specified, made it more clear. I am going to do it now here. A.1 omega is known, so I don't have to find omega. Okay. So we have a situation, two equations, 2 equations, 4 unknowns. What do we want to find? Indeed, I want to find P1, Q1, P2, Q2. These are the things I want to find. So I have to include more equations in my analysis. So far, 2 equations, 4 unknowns. Need more equations. What are those new? Where do I get those additional equations from? Euler's second axiom, and that's what I do in step 5 anyway while solving these problems. So I am on my way to get the new equations. Step 5, MESA, V2 version we have to chase. This equation will be written, all moments will be computed about C, valid point. Indeed, it is a valid point. C is the center of mass, always a valid point. What are those equations? Those equations are written many times before already. but there is no escape. Actually, every time you solve a problem, you will have to write this again. And why don't I write? After all, this gives me the solution. So since I am writing moments about point C, all these inertia components have to be found about C. Now, many terms in this are already zero. I know them to be already. Which terms? I have already been told that there is no omega dot. So I don't need to worry about these. Okay. And we are also assuming that IC23 and IC13 are known. The way I am solving this problem, it is for any shaped rotor of any shape. Of course, if you have to solve a particular problem in life, you will know the shape of the rotor, then only you can proceed with the solution. So whatever the case, for the time being, I say that IC23 and IC13 are known. Then I also know omega is known, so everything on the right hand side of these three equations is actually known. What is my next job? My next job is to find MC1, MC2 and MC3. To get MC of these components, I write the MC vector itself. If you go back, MC is what? Moment due to the external force system about C. Let's look at the FBD. What all will contribute to the moment about C? Mg is not going to contribute anything. Mg is passing through C. P1 and P2, Q1 and Q2 will indeed contribute moments. And while I try to write the expression of that net moment, we will have P1, P2, Q1 and Q2 appearing there, obviously, because these are the forces which will contribute to the moment. Also, I am going to use some lengths to express those moments. This L1 will appear, this L2 will appear, and this R, the offset of center of mass from the IAR, that will also matter. I'm not going to redraw the figure on this slide, but I'm going to write the expression of MC directly. If you are reading my notes, just go back 2 slides ago, see the picture there, diagram there, and convince yourself that my expression is written correctly, what I'm going to write. If you're watching my video, you need to pause the video, go little back, you can see the free body diagram and then verify what I'm going to write is correct. Okay. So MC will be written as RPC cross force P plus RQC force Q. Mg does not contribute, passes through C. Now what are these P vector and Q vector? They are these net force vectors, which I can easily write in terms of P1, P2 and Q1, Q2. RPC is minus L1E3 plus R times E2, whereas RQC L2E3 plus R times E2. Verify. So if you replace these vectors from here to here, MC turns out to be writing the final expression, skipping some steps. I believe they are very straightforward. L1 P2, L2 Q2, so along E1, something along E2, okay. So let us equate this star to double star here. Star is the left hand side of the double star. So if we match coefficients, three equations we will get. Three equations, three scalar equations. Those three scalar equations are call it equation number 4. Why I call equation number 4? Because I had three equations here. The third one is of course trivial, but for the sake of it I number it as 3. So I have, maybe I just leave the numbers here as 1 and 2. P1 plus Q1 is first equation, P2 plus Q2 equals this is second. So strictly speaking, I should call this equation number 3, the third non-trivial equation, not 4. L1 P2 L2 Q2 IC23 omega square with a minus sign. Then I get an equation and finally I get the equation P1 plus Q1 P1 plus Q1 times R equals 0. This is the fifth equation. Fifth equation. Again, how many unknowns we are dealing with? 4. Are we getting an excess number of equations? Looks like, but let's recheck. This equation is effectively P1 plus Q1 equals 0. Now if you go back and check the first equation here on this slide, that is also the same. So equation number 1 and 5 are the same equations. So at the end of the day I am getting only 4 independent equations. Four unknowns. Independent equations are number 2, number 3 and number 4. Number 2 is coming from slide number 20. And this is of course from slide number 22, the current slide. We can solve them, which I can call as my next step 6. Step 6. Solve for these unknowns. I have the solution already with me on my notes. I'm going to write it. Of course, your job is to do this exercise and make sure you get the same answer. My answers are the following. Please verify. So I have solved the problem. What has been asked? What was asked? Find the reaction force system at P and Q. That's what they asked me to find. I have found. Now I come back to the primary questions, primary motivation why I did this analysis. I wanted to define what is dynamic reactions, and I want to talk about rotor balancing. So now let's use this result. In the light of these results, let us try to understand what these two things are. Okay. So we do. What do we mean by dynamic reaction force or dynamic reaction torque? Rather, I would like to straight away define what is meant by dynamic reaction force system. So we understand what is a reaction force system at a given support, or the reaction force system generated by a given support. The dynamic reaction force system is that part of the reaction force system that depends on motion, the motion of the RB. That's the definition. When the motion stops, dynamic reaction force system will go to zero. Dynamic reaction force system. Let's use this acronym DRFS. This is the definition of DRFS. Now you will realize that for a given problem at a given instant, the total reaction force system will not be the same as what I am calling as the dynamic reaction force system. And thus, there will be a difference between TRFS and DRFS. And this difference is called the static reaction force system. SRFS. In the last problem, what did we find? P1, Q1, P2, Q2. There are four forces, and these four forces make a force system. They make a reaction force system, right? Because they all are coming from the reaction generated at the supports, right? So for this problem, which I solved, DRFS is, for the last problem, TRFS is, total reaction force system is P1 E1, P2 E2, Q1 E1, Q2 E2. You can call this as the TRFS. What is the DRFS? To identify what is DRFS, you have to look at this solution. Look at P1. what will happen to P1 if the motion is stopped? Motion of what? Motion of RB is stopped. What is representing motion in this expression? Motion is being represented by omega. So if I make omega as 0, what will happen to P1? P1 will be gone. By my definition of DRFS, P1 is a part of DRFS, dynamic reaction force system. What happens to Q1? Same thing. If omega goes to 0, if I do an experiment with 0 omega, Q1 will be 0. And that's why Q1 is also part of DRFS, dynamic reaction force system. Come to P2. If I set omega to be 0, what happens to P2? A part of P2 vanishes, but a part of P2 is retained. The part of P2 which will vanish because of omega vanishing will be part of DRFS. And the part of P2 which is not vanishing despite omega being 0 will go and become SRFS, part of static reaction force system. Same thing goes with Q2. It has both DRFS and SRFS sitting there. This term and this term will make dynamic reaction force, whereas the one which does not have omega involving mg will become static reaction force system. So let's go and tabulate this for clarity. I have prepared a table here. Rotor rotating with constant omega, last problem. Looking at the solution, reference is slide 22, solution. At P, what is the dynamic reaction force? This is the dynamic reaction force. Along E1, there is no dynamic reaction force at P. Just the other way actually. I should. So this column is supposed to be for static. Let me make it consistent with my notes here so that I don't end up mixing up things. Dynamic. Okay, so what I was saying, 0 along E1 is actually static. 0 E1, mg L2, L1 plus L2. That is along E2. So part of reaction force at P becomes static reaction force, and the other part goes and becomes dynamic. The dynamic part is okay. If you go back and look at the solution, I'm talking about this part now. Okay, along E1 I get this force. Along E2, dynamic will be comprised of this and this. There are two parts. C13 omega square L1 plus L2 E1 plus I see 2,3 omega square plus m omega square or L2 L1 plus L2 E2. At Q, the static force is 0 along E1. Along E2 it is mg L1 plus L1 plus L2. Whereas here I have IC13 is equal to 3 omega square plus m omega square or L1 is equal to 3 omega square E1. Plus m omega square or L2 This is the segregation. As I said earlier, you look at this column, you set omega to be 0, everything vanishes. That is the evidence that all these reaction forces are dynamic reaction forces. Whereas on the other column, the first column, oblivious of omega, whether omega is there or not, the static reaction force remains the same. Okay. So these are the results for this problem, of course. But in general, for any dynamics problem, you can categorize the reaction force system based on this understanding. In fact, in the book Beer and Johnston, which is one of our reference books, there are many problems in which they ask you only to find the dynamic reaction force. They don't even ask you to find the static reaction force. You will realize that if you are asked to find only the dynamic reaction force, you can follow the same procedure what I did and assume mg is non-existent. Solve the problem following my procedure. My steps. You get dynamic reactions directly. I mean, whatever reaction force system you will get, that will be dynamic. System you get, that is DRFS directly. So this is sort of a trick. If you are being asked to find DRFS, simply assume that mg does not exist and go ahead and solve the problem exactly the way I have solved. You get DRFS. But if the problem says find the reaction force system, what they mean is total reaction force system, which I am calling as TRFS. And to get TRFS, you will have to include mg also, just the way I did, and then get answer of this sort, what I got here, where there is a mix of mg and there is motion also. Okay, so pay attention to what is being asked in the problem. This has been clarified to you. Keep that in mind. Assume mg is non-existent, solve the problem. Okay, so this answers one of the questions that I raised in the beginning of this lecture. What are dynamic reaction forces? I have given the definition, I have given illustration using an example. There was the second question. Balanced rotor. What do we mean by balanced rotor? I'll take 5 more minutes, complete this topic, we can have a break. Balanced rotor. What is a balanced rotor? The concept of a balanced rotor is based on the fact that dynamic reaction forces are typically undesirable forces. Why they are undesirable? They are undesirable because they cause a lot of vibration in your rotor. The dynamic reaction forces will keep changing their direction. If you go back and look at this free body diagram that I showed, you look at this free body diagram, P1 is oriented along E1, P2 is oriented along E2. Similarly, Q1 and Q2 have their orientations along E1 and along E2. But then remind yourself that E1, E2 and E3, or rather the axis X1, E1, X2, E2, X3, E3 are all fixed to the body. It means that as the body rotates, the orientation of the three axes will change. At least x1e1 and x2e2 will change, and correspondingly the orientation of these forces, non-zero forces, will keep changing. Okay. So because of this changing direction of the reaction forces, there is a tendency for the rotor to develop vibration. DRFS may have fixed directions with respect to the M frame. They do have fixed directions, but their directions keep changing with respect to ground. Causes vibration in the system. Undesirable most of the time. Typically, I have shown some pictures here. Any of you who drives a car, who has a driving license, you might have experienced what I am going to talk about in with reference to these figures. The first figure I am trying to show that if your wheel, mind you, a wheel is a rotor, it is actually a rotor, it can be modeled as a rotor. So you have this wheel of your car, it is mounted on this axle and this rotates. Okay. Sometimes if the car is not well maintained, or if the tires are very old, if you go to high speed, 80-90 km an hour on a highway, you will feel a vibration on the steering. That vibration is coming because of the dynamic forces, the sort of dynamic forces, the expression of which I have derived here. So these reaction forces are changing their direction, and that's why you get vibration. People talk about balancing a wheel. This is part of the maintenance of a car. Nobody likes the steering wheel to be vibrating when you go to high speed. Interestingly, you may not experience this while driving in traffic in a city because the omega is small. Okay, only when omega becomes high, the change in direction of these dynamic forces become very rapid, and that is why you start getting perceivable and annoying vibrations. You take your car to a garage, workshop, and they do what is called wheel balancing. They will take the wheel of your car out and put it on a machine like this. Okay, what does this machine do? This machine suggests the mechanic that he needs to put a certain amount of mass, very small, certain amount of mass, which is typically small in size, and the machine tells the mechanic that he should go ahead and fasten that small mass on a particular location on the rim of your wheel. And if the mechanic does a good job, you will experience that next time you are on the highway, the vibration will be gone. I would say that the wheel has been balanced thanks to the mechanic. While your mechanic may not know how exactly it works, we as engineers here are supposed to know how it works. And let me explain to you what is actually happening when he puts it on the machine, and what happens when he puts a small amount of mass at a certain location on the wheel. To get rid of vibrations, you need to get rid of DRFS completely. How do we get rid of the DRFS? One is, of course, you don't drive the car, or you always drive the car very slowly so that you are not disturbed. That is not a question under consideration. I want to drive my car at 100 km per hour and I don't want any DRFS. So omega being not equal to 0, how do I get DRFS to be 0? I have written the expressions for the DRFS again from the previous slide to this slide. We have to kill each and every component of DRFS here. Let's focus on this. How do I kill this? Let me call it 1, 2, 3 and 4. 1 and 2 can be made 0 if your IC13 is 0 and omega is not 0. Even then it will take us home. Pay attention to the expression there. IC13, if you ensure, is 0. 1 and 2 will be gone. 1 and 3 will be gone. Talking about this and this. I also have to kill E2 components here, 3, 2 and 4. Now it may appear to you that I can kill IC23, I can kill 2. 2 can be made 0 if IC23 omega square becomes equal to minus m omega square R times L2. I'm talking about this expression here. 2 will be killed and 4 will be killed if IC23 omega square equals minus of m omega square R L1. Mind you, omega is fixed. You do not have a choice. Omega fixed. M is fixed. L1 and L2 are fixed. The only way to have both 2 and 4 0, you can verify that will happen only when R is 0 and IC23 is 0 independently. So how many conditions do I have? I have 3 conditions identified: IC130, IC230 and R equals 0. These are the necessary and sufficient conditions for having a balanced rotor. Balanced rotor, constant omega. Your center of mass should be on the IAR. IAR must have CM lying on it. And IC13 should be 0 and IC23 must be 0. In other words, X3E3 must be a p-axis of RB at C, which itself must lie on the IAR. This will implies DRFS is 0. I stop here, we'll come back and meet again at 5:10.